Hello everyone. So today we are going to be talking about inhomogeneous flows. We've been talking about homogeneous turbulence at length and what was the cost associated with it, and at where we spend most of our cost on, isn't it? Where is most of our effort spent on? But as you know, homogeneous turbulence is a very idealized form of turbulence. You have a box with periodic boundary conditions. You will never have a practical flow with that kind of boundary conditions, isn't it? Or even that kind of problem. But homogeneous turbulence presents a very nice problem to assess very simple things. One related to the numerical method, as I was saying in the last class, related to accuracy, related to the cost, the spectrum, things like the Kolmogorov length scale, Taylor scale Reynolds number, all that is very straightforward in homogeneous flows. That said, all practical flows, in fact, none of the practical flows have homogeneous turbulence. So it is imperative that we talk about inhomogeneous flows and have a discussion related to it. So as we were talking about DNS earlier, the high cost is motivated by several approaches because of attaining the high Reynolds numbers, right? So what we do is, since DNS has a very high cost associated with high Reynolds number flows, and it keeps increasing as the Reynolds number is increasing, we have to look for additional approaches where we don't have to spend most of our effort on the scales related to the dissipation range. Maybe we can spend most of our effort where the most of the energy is contained in, which is the energy containing range, and a little bit in the inertial subrange. So one such approach is LES, and we have discussed briefly that. In fact, in the next module, it is exclusively talking about LES. But in LES, what happens is we resolve all the large length scales and we model all the small scales. So we are not going to be spending as much time or effort on the scales in the dissipation range, or in fact no time. In a sense, we are spending no time on resolving the scales in the dissipation range because we are completely modeling that. And that is clear when I showed you the plot from the last class, when you saw this earlier, where there is this small circle and a slightly larger circle that are associated with the energy containing range and the inertial subrange. This large circle, all of this is related to the scales in the dissipation range. Now, in LES, you would only do this. That's it. You would only resolve there. Everything else is modeled. So you can imagine how much time and effort we are going to be saving. So that's what the basic concept of LES is. Now, in wave number space, the number of discrete wave number modes of magnitude, kappa magnitude, less than kappa increases as kappa cube. So because of this, in a fully resolved DNS, the vast majority of modes are in the dissipation range. That is why you have a vast majority of modes in the dissipation range. Now, this is a strong motivation for approaches that reduce resolution requirements. So what if there was an approach where we didn't have to resolve all those length scales? So that is the motivation for coming up with an alternative approach where you can reduce the resolution requirements in the dissipation range, especially if the energy containing range motions are of primary interest. Why are they of primary interest? Because most of the energy is contained in there anyway. So why don't we just resolve all the energy containing scales and a bit of the inertial subrange? So that is what LES does. In LES, only the energy containing motions are resolved, and the effects of the unresolved modes, that is most of the inertial subrange and the dissipation range, those are modeled. Meaning you have to have a model that can resolve all those length scales. You have to have a model that can model all those length scales, not resolve, model all those length scales. So compared with homogeneous turbulence, the principal differences in applying DNS to inhomogeneous flows are, one is obvious, the fact that we cannot use Fourier representations now, because you no longer have periodic boundary conditions, because you have directions of what we call inhomogeneity. We are talking about homogeneous turbulence versus inhomogeneous flows. Homogeneous turbulence means what? Nothing is changing with respect to space. So periodic boundary conditions can be applied. You can consider the flow to be periodic. Nothing is changing with the statistics are not changing with respect to space. You have exactly one point, in a sense. You have exactly one point. So periodic boundary conditions can be applied. There is no flow in reality that is like this. No application flows are like that. So that means we are talking about inhomogeneity. So the Fourier representations won't be applied, won't be appropriate because they are not periodic. So that is one thing. Second, you now have physical boundary conditions. What are physical boundary conditions? Walls, no slip boundary conditions, right? Flows where problems where flows are coming in through, say, a nozzle, like in a jet. Flows where where you have the velocity or fluid coming in through a channel width. Those are not there in homogeneous turbulence. So those are physical boundary conditions as opposed to periodic boundary conditions in homogeneous turbulence. And then third point is this near wall motions impose additional resolution requirement. What am I talking about here? So if you have even just take flow over a flat plate. Okay, flow over a flat plate, I have the no slip boundary condition, so U is equal to 0 here, which means the layer right above the wall has a finite velocity. The layer on the wall has a 0 velocity, but the layer right above the wall has a finite velocity, which means there is going to be a velocity gradient here. That is how we know that if you have a velocity gradient, it's going to look like this, isn't it? Which means you need to resolve that velocity gradient. So in terms of grid points, if you have your wall, you have to have an extremely fine grid near the wall. Whereas as you go away from the wall, you can afford to be coarse. So near the wall, it is going to be very fine. So that kind of resolution requirement in order to resolve the velocity gradient near the wall is what I'm talking about. These near wall motions impose additional resolution requirements. In homogeneous turbulence, that is not the case. You have a box, there are no walls, there are no additional resolution requirements to be to account for near some kind of boundary or in a particular location. The resolution requirement everywhere is the same in homogeneous turbulence. So that means you can have a uniform grid in homogeneous turbulence. Whereas in inhomogeneous flows, you might have additional requirements because of the presence of something like a wall. So that additional resolution requirement can create a lot of issues, right? You will need to have a grid that is very fine near the wall. So suddenly, when you're talking about more grid points, you're not just talking about more grid points away in different parts of the domain. You're talking about additional number of grid points in order to resolve the velocity gradient near the wall. So additional, say, wave numbers, if you are considering spectral methods, although spectral methods cannot be considered because of the fact that you have inhomogeneity and you don't have a periodic boundary condition. But conceptually, it is the same as including additional wave numbers. So one additional point here, in DNS of channel flow, which was performed by Kim et al. In 1987, those are some seminal data that are still used for validation for different codes. What they did was they had a domain, a rectangular domain that was of the size Lx by h by Lz, where h is actually the channel width. Lx and Lz are the lengths in both the other directions. The flow was considered to be statistically homogeneous in the two directions, as in the directions that were not wall normal. So if we had a domain like this is the wall normal direction, so this is h, this is Lx, for example, and this right here is Lz, for example. So the span-wise direction, the mean flow direction was, so the flow was in this direction, so that is Lx, and LZ was in the spanwise direction. So this way, what he did was, because he was able to assume the flow to be statistically homogeneous in the x and z directions, he could use Fourier representations in those two directions. And in the wall normal direction, he used a Chebyshev representation with ny modes. So nx and nz mode, so he was able to use a Fourier representation in the two directions. So he was still able to use spectral methods for the two directions. And because the wall normal direction, because it is not periodic, obviously, he had to use a Chebyshev method in the wall normal direction. So that's an example where you can still get away with using Fourier representation in one or two directions by assuming one or two directions to be statistically homogeneous. So some additional discussion here. So as you know, DNS provides a level of description and accuracy that is unparalleled. No other method, no other approach can match the accuracy of DNS. And naturally, that is why DNS is just much more expensive than any other method that is out there. So, for example, DNS can be used to extract any kinds of statistics, even Lagrangian statistics, because you have information at all points in space at all times. So that means you can extract Lagrangian statistics as well. You can extract two-point correlations. You can extract rate of strain tensors. Anything is possible using DNS calculations because of the amount of information that is already available. Details of near-wall flows and homogeneous turbulence subject to various deformations are also easily available in DNS, just like in experiments. Now, in fact, one can argue that some of this information is much more easily available in DNS than in experiments, because in experiments the logistics of obtaining these statistics because of additional cameras, additional resolutions is going to be much more. Whereas in DNS, as long as you are resolving all the way down to the Kolmogorov scale, and I'm only talking about homogeneous turbulence, because I know that homogeneous turbulence is a relatively simple problem to do in terms of it's simply solving the Navier-Stokes equations, it's solving using the spectral methods which are the most accurate, and it is resolving all the way down to the Kolmogorov scale. So in that sense, all kinds of information, like for example, various deformations and details related to near wall flows, all of that is easily obtainable in DNS, even compared to experiments. So, but all that said, not all simulations based on Navier-Stokes equations are direct. Yes, when we are solving the Navier-Stokes equations directly, we get the we are solving it without any other specification. True, but there is an additional catch here which we had discussed earlier. There is the whole idea of getting the right boundary conditions from the experiments, and sometimes that is not easily obtainable. Getting the right boundary conditions may not be straightforward. I had given examples where trying to get the jet velocity coming out of a nozzle from experiment is not possible. Is not that easily possible, because when you get the mean might not be enough in order to trigger it to turbulence. Then you have to specify some additional fluctuations. Where do you get those fluctuations from? Can those fluctuations be obtained from experiments easily? So all those complications arise when you're talking about boundary conditions. So not every problem can provide the boundary conditions easily from experiments, and sometimes you have to make some approximations. When you make approximations, comparisons between computations and experiments may not match as well, so then you have a problem, right? So that's what we mean by not all simulations based on Navier-Stokes equations are direct. They are direct only to the extent that you're solving the equations exactly, resolving it to the finest scale. But there is still a matter of the boundary conditions. Where are you getting that boundary conditions from? Are they exact? So only when those are exact does it become fully, completely direct. I hope you're following me here. So the drawback of DNS is obviously the fact that the cost is very high, and the cost increases significantly as RE cube. And with regard to the computational cost, it is more than the limitations of the current computers, right? It is not just the fact that the cost is high. Most of the cost is spent on scales in the dissipation range, where there is very little amount of energy. So in order to capture the scales that are associated with such a small percentage of the energy, you are spending most of the effort. So it's like, in a way, one way to put it is that you are spending 90% of the cost, and I'm just putting out a number there. You're spending 90% of the cost to resolve 10% of the energy. Isn't it? So the question will always remain, can't you just spend 10% of the cost on capturing 90% of the energy? So like a 90-10 rule. Again, those numbers are arbitrary right now. Those are not exactly the same. Those are not correlated exactly, but I'm just, as an example, I'm telling it to you. 90% of the energy is spent on 90% of the effort, cost is spent on 10% of the energy, on capturing 10% of the energy. So why not just spend 10% of that effort on capturing 90% of the energy? So that is with regard to DNS. So that takes us to our turbulent viscosity models, which is where our hypothesis comes up, the turbulent viscosity hypothesis. So as you know, the Reynolds stresses, in order to get a closure for the Reynolds stresses, business came up with the turbulent viscosity hypothesis. The turbulent viscosity hypothesis, like the name says, it's a hypothesis, there is no proof. It is based on the hypothesis, which looks like this. The Reynolds stress is given by 2/3 K delta Ij being the Kronecker delta, minus nu T times this mean strain rate. We have discussed this multiple times. So here what we are saying is that if you can estimate the Reynolds stress as a function of the mean strain rate, then you can achieve closure. You still have the matter of specifying what the turbulent viscosity is. That is where the turbulence model comes in. The specification of the turbulent viscosity comes in through the turbulence model. The mixing length model has a different specification. The K epsilon model has a different specification. But we have talked about this multiple times, right? This is the turbulent viscosity hypothesis. Now, unfortunately, the accuracy of this hypothesis is very poor, and we'll discuss that in detail with an illustration of a problem as well. So if you accept the turbulent viscosity as an adequate approximation, then all that you need, okay, so let's say you accept the turbulent viscosity hypothesis, then all that you need now is the specification of the viscosity, as I was saying earlier, the specification of the turbulent viscosity. Now you can write that, just dimensionally you can write that as some kind of velocity and a length, U star, L star. And this is exactly what the mixing length model is based on. The algebraic based mixing length model is based on. So in the algebraic based mixing length model, the L star is specified on the based on the geometry of the flow. Basically a fraction of the characteristic length scale. That's it. Then you get an estimate for the nu T, you substitute nu T into your turbulent viscosity hypothesis, your equations are closed. In another example, like the K epsilon model, the two equation model like the K epsilon model, U star and L star are related to K and epsilon for the model transport, and then the model transport equations for K and epsilon are solved. You get an estimate for L star using K and epsilon, and you get nu T. You put in nu T into your turbulent viscosity hypothesis. There you go. Your equations are closed. So that specification of the turbulent viscosity hypothesis becomes the next play, right? If you accept the turbulent viscosity hypothesis as accurate. But we know that that is not accurate, and that is what we are going to be dealing with. So the turbulent viscosity hypothesis can be viewed in two parts. One, there is an intrinsic assumption that the Reynolds stress anisotropy, Aij, is determined by the mean velocity gradients. That is your first assumption, isn't it? The intrinsic assumption that your Reynolds stresses, in fact the anisotropic part of the Reynolds stresses, is related to the mean velocity gradient. That is what we mean by this, right? Ui uj minus 2/3 K delta Ij is nu T times this. So it is proportional to the mean strain rate. That is your first assumption. Now the second assumption is a more specific assumption. The specific assumption is that the relationship between Aij and delta Ij is given by this particular relationship. Okay, so the intrinsic assumption was that it is just proportional to the mean strain rate. The specific assumption is that it is equal to, now it is more specific, not just proportional, it is equal to νt times the strain rate. So essentially, Aij, the anisotropic part of the strain rate, is minus 2 νt Sij. So this, as I was explaining multiple times earlier, this is directly analogous to the fact that your Newtonian stress is proportional to the strain rate, right? Isn't it? Tau Ij plus P delta Ij divided by rho, this is basically pressure. Delta Ij divided by rho is 2 nu Sij bar, and this is applicable to laminar flows. What Business did is he took that into turbulent flows. And because it is in turbulent flows, you have to say that it is proportional to a mean strain rate, because things are fluctuating, things are unsteady, isn't it? So two assumptions: an intrinsic assumption where you're saying it is proportional to the mean strain rate, and a specific assumption where you're saying it is equal to νt times the mean strain rate. So in order to see the limitations, the drawbacks of this assumption, of the intrinsic and specific assumption, let's look at this particular problem. Here, this is basically a grid turbulence experiment. So essentially, you have a turbulence generating grid here, which is actually a physical mesh through which flow goes through. There is a contraction, there's a straight section followed by a contraction, and then followed by another straight section. And we are going to see how this intrinsic and specific assumption apply here. So the air flows through this turbulence generating grid into the first straight section, in which the mean velocity is ideally uniform, isn't it? Because there is no contraction, so the mean velocity is going to be uniform. As once all the transients have passed, the mean velocity is going to be uniform. So that means there is no mean straining. Okay, there is no mean straining, and the turbulence begins to decay because there is no mean straining. In the experiment following the contraction, there is a second straight section. Since there is no mean straining in this section, the turbulence viscosity inevitably predicts that the Reynolds stresses is 0 here. What do I mean by it? So Sij mean is going to be 0 here in this straight section. As the flow is coming in, the mean velocity is 0. Now, according to your turbulent viscosity hypothesis, it is going to predict that the Reynolds stress is 0 in this section as well, because in any straight section, the Sij is going to be assumed to be 0 there, because the mean velocity is 0. Okay, we are talking about steady state. However, what happens is, in experimental data, what happens is the anisotropy generated in the contraction, where the anisotropy generated in the contraction does not make the mean strain to be 0 in that second straight section, because they decay quite slowly based on a turbulent length scale, based on a turbulent time scale, I'm sorry. So these persisting anisotropies exist not because of the mean strain rate, but because of the prior history of straining to which the turbulence has been subjected, because of the prior history. So for this flow, in the contraction and in the straight section, the intrinsic assumption becomes incorrect. Here it was okay, but once it passes through the contraction, the anisotropy causes turbulence which takes some time to decay, right? It is not going to be decaying immediately. Whereas what we do with the intrinsic assumption is that we say if the mean strain rate is 0, boom, your Reynolds stress is 0. Whereas in reality, that is not what happens. It takes a little while for the turbulence to decay because of this contraction. And so there is a history associated with it. That history, that turbulent history, decay history, is completely neglected in this intrinsic assumption, because what we are saying is that it is dependent only on the local mean strain rate, whereas everything is not local. There is a history associated with it, and that is what the turbulent viscosity hypothesis neglects. So the specific assumption that the Reynolds stress anisotropy tensor is linearly related to the mean of the simplest flow is just going to be simply incorrect. It's just going to be incorrect, because it is not equal to nu t times this thing, right? That comes from laminar flows, the fact that it is equal to viscosity times mean strain rate. But the intrinsic assumption itself is wrong, and the specific assumption is also wrong. So in laminar shear flows, for instance, the straining is very weak, and therefore it produces a very small departure from isotropy. So there is every reason to expect that the anisotropic stresses depend linearly on the velocity gradients. And that is what we have the Newton's law, right? That Newtonian stress is proportional to the strain rate. That is possible, because that history does not have, those timescales are very large. So if those timescales are so then it does not have as much history of and the contraction creating. If it was laminar flow through that contraction having a prior history and causing the mean strain rate to be not zero, that does not happen for laminar flows. However, in turbulent shear flows, the rate of straining is very large and leads to relatively large anisotropy. So there is no reason to assume that that relationship is linear, meaning it is a linear relationship between stress, turbulent stress, and turbulent strain. And in addition, there are several classes of flows in which the mean velocity gradient is much more complex than in a simple shear flow. And in those cases, this turbulent viscosity hypothesis would just not hold at all. So those are the limitations with the turbulent viscosity hypothesis, which we have seen through an example problem like the shear flow problem. So what we have done in this class is in this module is that we have looked at the challenges and modeling approaches, right? We have looked at what were the different criteria for appraising the model. We looked at the different criteria. Then we moved on to direct numerical simulation and saw what was the cost associated with it if we do a fully accurate DNS, and where most of our cost is spent on. That led to, because looking at how much cost is spent on resolving the scales that are in the dissipation range, that led us to think that we need to come up with alternative approaches like LES that spend most of their cost on the large scales. And especially and then we had some discussion on inhomogeneous flows as well, where the simple periodic boundary conditions wouldn't apply. More complications arise, like wall boundary conditions, which would complicate things more. Finally, we discussed the turbulent viscosity hypothesis and how the intrinsic and the specific assumption related to the hypothesis was wrong, especially when in the context of this particular problem. If it is wrong in the context of such a simple problem, it is wrong in the context of many other problems as well. Okay, and so we tried to bring that out through a simple example. So I hope this module was clear. In the next module, we'll be talking exclusively about large eddy simulations, or LES. Thank you.